Behavior trees. These are probably the most prevalent AI behavior framework in all of game development. In this video, we're going to implement an enemy AI with 4 different attacks with a behavior tree so you can see the full process end to end when we have absolutely nothing besides our behavior tree framework. Hey, Chris here from LlamAcademy, here to help you.
Who? Me?
Yes, you! Make your game dev dreams become a reality by giving you a full walkthrough of an enemy AI with a behavior tree. Let's set a little bit of expectations real fast. In this video, we're not going to implement a behavior tree ourselves, so we're not doing like how to make a behavior tree. That's not this video. What we are going to be doing is taking a behavior tree framework. Specifically, I'm going to be using a paid one called AI Tree that was gifted to me by the developer Renowned Games. It wasn't a perfect experience, but I did really enjoy using it. And actually, after I implemented this whole video and did the whole thing, I went and re-implemented this with Opsif's behavior designer, and I really liked AI Tree better. You can do these same things with pretty much any behavior tree framework. Every behavior tree framework is going to have a little bit different flavor of how you do things. But if you are interested in AI Tree after we go through this video, I've got a link in the description to that asset. And again, I had a really great time using it. Now, what we will be doing in this video is implementing an enemy AI, a llama that's going to chase our player. It'll go idle when the player's too far away. It'll spit at the player when it's within some range, do 2 different types of melee attacks, and have a gap closer. If that sounds extremely familiar to you, that's because we did this exact same thing with a finite state machine a couple of weeks ago. If you haven't seen that one and you're interested to see the comparison, I've got a link to that video in the description as well. And just one last thing before we jump in, if you're not sure which enemy AI behavior framework to use, I've got a video where I compared finite state machines, behavior trees, GOP, and even unstructured AI that I'd highly recommend you check out if you're not sure which one would best suit your needs. And without further ado, let's hop into the implementation.
Let's start off by taking a look at this llama. This is a paid asset from these guys. I don't know how to say that. I'm not even going to try. It comes with quite a few animations. This means that we have attack, some different variants of attack, a way to walk, some idle animations, and a way to roll, which is obviously something that we need to have for a llama. In the animator, we're not having anything hooked up here, so we're just going to crossfade between these different animations whenever we want to move from one state to the next. There's really 2 main components that go into making the behavior tree. There's the behavior tree itself, and there's what we call the Blackboard, where we'll post values there and the behavior tree will read it. So in our project panel, what we can do is right click, create Renowned Games AI Tree Blackboard, and also a behavior tree in the same place. If you just double click on both of these, it opens up 2 different windows. I'm going to dock those together and also add in a couple other important windows that we're going to want to use as we define our behavior tree on our Blackboard. To the top, we go to Renowned Games, AI Tree, Windows, Node Inspector. We'll dock that to the side. The last one will be Key Details, at least for now. Every behavior tree framework has more or less these same components. They're just maybe designed a little bit differently. If we maximize this, so it takes up our whole space, we can see it comes from a root node. Whenever the behavior tree is being evaluated, it's always going to come from the root node and then basically pick from left to right in priority order, which state should we go to. With AI Tree, we can press space to get something. It works really similar to ShaderGraph if you ever use that. You get nodes with some submenus. You can choose what you want to add, and they're all grouped by what type of thing it is. You can also drag from the bottom of this thing and give you that same menu, and it'll, I don't know, let's just click wait, and it'll create that line for you. You can delete them as well just by pressing delete. So I like to start with the least important thing first, so that way we always have something that doesn't really have any conditions to go to, which is generally speaking the idle state. So from the root, we'll want to go down, and in our case, we're just going to select from a range of things to do. So for that, it's under composites, it's a selector, and then we'll have several things beneath it. If we start with idle, come over to the side, again, composites, sequencer. So selector picks something based on whatever conditions are available. Sequencer will run things in order. So the first thing I do in idle state is going to be play an idle animation. So we can do that with tasks, animator, crossfade. And the way this one works is it will just crossfade to that animation state name, and you can provide different normalized transition time, layers, all this kind of stuff. I'm not going to worry too much about all these possible parameters. We're just going to go straight into playing the idle animation, which in my case is called idle_A. We can rename the name and we'll see it change here. Once we've played an idle animation, we don't want the tree to immediately reevaluate, right? Because then every frame we're going to come in here, or every tick we're going to come in here and crossfade over to play this animation again. So what we can do then is wait some period of time. In this case, let's just say we're going to wait 1 second just for fun. The value we put here should be at least the duration of this animation. We're going to do some back and forth just to be testing this as we go. If we select the root node, we'll make sure to assign that Blackboard, the Llama Blackboard. And you can choose how frequently you want this to update. We're going to leave it once a frame, which is on update. We save this, we'll minimize it. I'm just going to move it off screen. We'll bring it back and maximize it in a second. We select our llama. You need to make sure you have a behavior runner attached and provide to it the behavior tree you want to execute. That's going to be our llama tree. And this enemy doesn't have anything in it right now, so we'll just disable it so we don't worry about anything else. It's just going to be the behavior runner that's running. If we click play, lo and behold, the idle animation plays. We can see because of my wait time isn't perfectly aligned to my animation that he kind of does a double bounce as he crossfades between them. If we select the llama, we can also see with the behavior tree as it evaluates, if you can kind of see it flicker, I hope that comes through on the recording, that's whenever the wait time has ended and we're reevaluating the tree to come to, hey, we're playing this animation and then moving over to the wait 1 second. Cool, so we can see exactly what's happening on the tree. That's a really nice benefit when we're trying to debug something. I'm going to go ahead and update the wait time to 1.25 seconds and hope we get a little bit less bouncing. I get asked all the time,
Chris, how do you know all this stuff?
and a lot of it comes from experience using Unity and doing development in general, but I had a really great start in college. And that's where I'd like to talk to you about today's video sponsor, Southern New Hampshire University, or SNHU. SNHU provides low-cost, affordable game development and computer science degrees that can help you level up your game dev skills. Many of you may not know, I have a software engineering degree, and I feel like it's added a lot of value just going to college, getting that degree, helped me understand how does software work, how do things like state machines work, for example, and how do video games work, which is why I'm partnering with SNHU to bring you information about how you can get a college degree from an accredited university with 2 accredited degree programs that I want to talk to you about today. One is a computer science degree, which is very similar to the software engineering degree that I have, and a game design and game development degree if you're more interested in specializing in game design and development. In that degree program, you'll learn things like what we talked about on this channel about how to implement things with gameplay, AI, physics, all of these things that we talk about on this channel. You'll get structured lectures from university professors who have real world experience. You can get either of these degrees online through SNHU at a really affordable price. If you're interested in learning more about these degree programs, you can go to snhu.edu/LlamAcademy, fill out the form there, and a real person will contact you to help you understand how these degree programs can specifically help you. Again, that's snhu.edu/LlamAcademy. Go there, fill out the contact form, and someone will contact you with more information about the specific degree program that you're interested in. Let's come up with the next state of chasing the player. That's a good second state. In order to chase the player, we need to know where the player is. That's where the Blackboard is going to come into play. You see that we have on the Blackboard keys self, so we know our own transform. We can tell it's transformed because it's blue. We don't have a way to go to the player. We'll add that new key to the Blackboard in a second, but first, let's start designing this state, for lack of a better term. To chase the player, we'll probably do the same things we just did for idle, except move to the player. So we'll do another sequencer. I'm going to copy paste my animation. Play the walk animation. And then we'd want to move to the player, right? So let's go to tasks, nav mesh agent, move to, and here on the node inspector, we can see it's going to do some stuff. We can move to a transform key, looks like, but we don't want to move to ourselves. We want to move to the player. So we can go Blackboard, new key, transform. Transform key we'll call the player. So see it updates it on Blackboard. And now on our Blackboard key, we can select the player. We can have an acceptable radius. So this is basically like stopping distance type of stuff and including this. So we'll just leave it alone for the time being. In the advanced section, we have allow partial path, track moving goal, and go to last point on lost. I'm going to turn off go to last point on lost. So whenever the player leaves range, he's just going to stop moving. Track moving goal will make it so whenever the player moves, he will also keep moving. That seems pretty straightforward, pretty simple. But how do we know when we want to chase the player versus whenever we want to be in idle state? Probably the player needs to be within some acceptable range, and if they go too far away, we want to give up. So again, we'll do that with a Blackboard key, add a new boolean, and we'll call this one is in chase range. Now every behavior tree framework is a little bit different. With AI tree, it's really convenient. We can right click on a sequencer or one of these types of selector nodes, really can be any node, to add a decorator or a service. A decorator is like a preprocessor that happens before we get to this node, and we can do things like compare Blackboard keys, do a Blackboard condition, a bunch of different stuff. For this one, we're going to add a Blackboard condition, click on that, and say if is in chase range, is true, then we want to come here. If the player's not in chase range, then this will fail or be marked as false, and we'll come over to this one, which has no prerequisites. It's just going to execute if nothing else works. You'll also notice here we have this flow control. This is really important for getting out of wait states and this kind of stuff. If we notify the observer on a value change, and if I just say, I don't know, both here, we're going to see that it interrupts both whatever's going down here, and it's going to override any lower priority things. So if we're in the middle of this 1.25 second wait and this condition changes, we'll interrupt that wait immediately and reevaluate the behavior tree and come in and start playing the walk and moving to the player. The same goes for we'll stop chasing the player if he moves out of range, because this is going to get changed to false. And in this behavior tree so far, we'll come over and go back to idle. You can't interrupt higher priority things because they're higher priority and they're just going to ignore whatever you're doing. I'm going to turn on the autosave feature so I don't have to forget about saving. And this looks great, but we don't have a way to set this so far. Now there are ways to do this. We could do some like pre-processing here and do it all in the behavior tree using the built-in perception system from AI tree or using an environment query, something like that. I think that's going to get a little bit too much in the weeds of how AI tree specifically works. So maybe we can cover some of that stuff in a future video. So what I've done, and I don't want to focus too much on the script portion, but we are going to review this one because it's really important. We made a class called this Player Sensor, and if you recently watched the state machine video, this is the exact same script. This is a mono behavior we're going to attach to several objects underneath the llama, and all it's doing is raising events on player enter or on player exit whenever the on trigger enter, on trigger exit events are raised by the physics system. So it's going to have a sphere collider. That's a trigger that whenever the player comes in, it's going to invoke onPlayer enter, and whenever the player leaves, we'll raise the onPlayer exit event. If we open up a class called Enemy, this is going to be where we manage providing data to that Blackboard. So we need a few things. First is a reference to the player. Second is going to be a reference to that behavior runner, and then some player sensors for the different ranges. I'm going to go ahead and define all of those right now. So we'll have three different sensors, one for whenever the player is in chase range, whenever they're in spit range, and whenever they're in melee range. On start, we can hook up the chase sensor callbacks. That's on player enter and on player exit respectively.
To make this a little bit easier to debug, we're going to define a bunch of values underneath a header called debug and serialize some fields like is in chase range, is in spit range, and is in melee range. We'll set these values whenever we get these events from these sensors, and then we'll use these variables to set values on the Blackboard.
Since we're just going to copy paste basically the same thing for all these player sensors, I'm going to set them all up right now, and then we can use them much more easily in our behavior tree. Okay, on player exit, we'll set is chase range false, and on enter, we'll set is in chase range to be true. And we're going to repeat this exact same thing for is in spit range and is in melee range with the spit and melee sensors. So we'll just duplicate that chase sensor on player enter and on player exit twice. And anywhere we see chase in any of these words, we're just going to rename it to spit. And anywhere we see chase on the second set, we're going to rename it to melee. So we'll have melee sensor on player enter, melee sensor on player exit, and set is in spit range and is in melee range based on which function we're in. We've just done the exact same thing we did on chase, on melee, and spit. Cool. Now we have some Boolean tracking this kind of stuff. Probably the easiest way for us to set these Blackboard values is to just do it every frame. Again, it doesn't have to be every frame. You could do them in these events if you wanted. It's just probably a little bit easier to understand if we do it on update. We'll check that the behavior runner is null. If it is, we'll return because we don't want to do anything. We'll get a reference to that Blackboard, and we want to set the player position because we need that for the setting position. And we'll also set the is in chase range Boolean. We can do if Blackboard try get key player out transform key player key, which will return true if it can successfully find that key. This is just to safeguard you against setting a key that doesn't exist, much like try get component from the Unity API. That'll set us a value to player key if that's found, and we can just do player key.setValue to be the player transform. We do this exact same process for every single key that we want to set. So for is in chase range, we can do Blackboard try get key, is in chase range, out bool key, chase key. Chase key.setValue is in chase range. Great. Those are the only two that we need right now. So as we get to implementing some of the other ones, we'll come back and implement the rest of these. So now we can see is in chase range and player key should get set. Let's go ahead and move this off the screen again. In the Unity editor, we can enable enemy, make sure we hook up our player behavior runner and at least the chase sensor. And on the player, we've attached a player script that has nothing in it. It's just a script identifier. For the chase sensor, we can have this movement sensor that has a sphere collider that is triggered, it's a radius of 10, on a layer called enemy sensor. Some of the stuff was already done because I reused the same project as the enemy state machine video, so if you haven't seen that one and you're interested in state machines, you can go check that out. I've got a link in the description. If we go to project settings, we go to physics, enemy sensors here is set up to only collide with player. If you don't have any of these layers yet, you can go to tags and layers and add in player, enemy sensors, roll impact sensor, and enemy now. And in your physics, at the very bottom, you can configure it like this, where enemy sensors only collides with player, roll impact sensor collides with default and player, and enemy maybe collides with default, player, and enemy. Back in the scene view, attach player sensor to this movement sensor that just has that sphere collider is triggered true. Make sure it's on that enemy sensors layer, and then hook up that movement sensor to the chase sensor. If we click play from here, check that out. Llama starts immediately coming to me because it's noticed I'm in chase range. On the behavior tree, we can see that it's evaluating true. We're playing the walking animation and moving to the player. Great. Okay, before I get pushed off the edge, let me run away from this llama. He's kind of slow. So once I get to be about 10 units away, we'd expect him to stop moving. Boom, there he goes. Perfect. If we bring back the behavior tree, we can now see that it's evaluating. Blackboard condition set to false, so it's not hitting this. It is coming to the sequencer, playing that idle animation, and then waiting. If we want to view the Blackboard in real time, we can go to Renowned Games, AI Tree, Windows, Blackboard Viewer. Stock that, I don't know, here. So we can see the self, the player, and is in chase range is currently false. We move a little bit closer, we see is in chase range flips to true, and the llama starts moving. As we run away, we'll see it eventually flips to false, and right as that happens, he stops moving. Perfect. Okay, so far so good. Nothing too complicated, just providing values to our Blackboard. Let's consider a melee attack next. We're going to want to do really similar stuff to whatever we just did here, so we can Control-C, Control-V, get all that stuff repeated, drag it in, and instead of playing walk animation, we'll play the attack animation. We don't want to move anywhere, so let's remove that one. You'd probably want to play damage or something like that. So maybe you do a wait. Let's put in a value like about half the duration of the animation. Then you could do something like send a message. Say that the player should receive the damage, and for the value, send something like 10. I wasn't planning to do this, but let's do it at least once just for fun here. Then we can wait one more time for the other half of the attack animation duration. But right now we're checking if it's in chase range, and that's not really what we want. We want them to be in melee range. So we can go ahead and add a new key to the Blackboard, call it is in melee range. That's cool. If they're in melee range, they can attack. We can wait the duration of the attack, but maybe there's going to be more of a cooldown than just the attack duration. So maybe we need a second bool. We'll call it can attack. I like to think about most of the keys most of the time in a Boolean fashion. You don't have to do it this way. This is just my personal preference. You could do something like have on the Blackboard the attack delay and then compare times and do that kind of stuff. I just find this to be easier to handle in a script, but it doesn't have to be that way. So for our Blackboard condition for coming into the attack state, we want to check not if we're in chase range, but if we're in melee range, make sure that's true. And we need a second Blackboard condition. We can add a second decorator, Blackboard condition, make sure that's on value change, board ourselves and lower priority, can attack, and we want to make sure that's true. Now it's starting to get a little bit ugly, so I'm going to do two things. First is create a group, call it melee attack, drag all the stuff in there, do the same for chase, and idle. And they have this function called auto arrange, which makes everything really beautiful for you without you having to do anything. Awesome. That looks cool. We just now need to set can attack and is in melee range on our enemy.
It can get a little bit verbose here, right? If we have to have 4 lines of code for setting one value, or 4 vertical lines at least with this formatting. So what I want to do is make a new private void set Blackboard value that accepts a Blackboard argument, a string for the key we want to set, and then a transform or whatever type we're going to set here. And I don't really want to use generics just to keep this a little bit more understandable in case you're not super familiar with those, but you could also do this with generics if you were super advanced. So we'll take a transform for this player, call it just transform, and in there we'll just cut and paste what we had above and refactor a little bit so it sets the value from the argument we receive instead of directly the player transform. We'll remove the hard-coded player to use the key that was provided as an argument and rename player key to just transform key. Then in update, we can just call set Blackboard value, passing in the Blackboard, the player key, and the player transform. So it goes down to one line of code. We can repeat this process for the bool key, chase key. So if we just cut that whole if statement, duplicate our set Blackboard value, and in our new overloaded Blackboard value, we can again remove our hard-coded is in chase range to accept the key and update our input type from transform to a Boolean. Finally, chase key.setValue should instead be the bool value that's passed in, and chase key probably doesn't make sense, so you can rename that to bool key or something like that. Back in the update, we can set the Blackboard value, again, single line of code, passing in is in chase range and then is in chase range, and since we're providing a bool, it's going to go to that second implementation of set Blackboard value.
It's a lot easier than copy pasting all the ifs and making sure everything's aligned. We're just changing two little sections.
So to do our attacks, we can again do set Blackboard value, doing for is in melee range and passing is in melee range.
Same can go for can attack.
Let's actually call this can melee.
Now, how do we know we can attack? Well, we're probably going to need to know the last time we attacked and compare that to some kind of attack cooldown. So back up at the top, maybe we can do an attack configs. And normally I would recommend putting this into like a scriptable object, but that's going to be maybe too heavyweight for this tutorial. So we're going to do basically everything in this one class. If you've been watching the AI series for a long time, you already know how we would do this. If you haven't been watching the AI series for a long time, I'll link to some videos that have maybe a more scalable way to approach doing this type of attack configuration. Put a melee cooldown, put it as 2 seconds with a range from 0 to 5, so we get that little slider in the inspector. We also need a last melee time that will just serialize beneath our debug stuff so we can see it in the inspector. For can melee, we'll just set last melee time plus melee cooldown is less than or equal to time.time. Then we need to set last melee time when something happens. We're going to use the send message functionality. We'll just define a function called onMelee and set the last melee time to be time.time in there.
The last thing in this class, at least for now, is we're going to want to comment out the spit onPlayer enter and onPlayer exit events because that's actually throwing an error right now. We didn't see it earlier because it didn't impact anything, but since the melee one comes third, we'll actually never reach there because we're going to get a null reference exception when we try to assign these events. If we come over to the player class, remember that we were sending a message on damage to the player, passing in how much damage they were going to take. So we need to define that on this player class.
Let's give ourselves a lot of life, so hopefully we don't die.
We can define that on damage as a public function that accepts maybe an int damage.
And we can just do health minus equals damage. We're not actually going to have the player die or go away or anything like that. We'll just check out his health in the inspector. In our behavior tree then, we'll copy the send message node, make the receiver be self instead of a player, and we'll just call onMelee. Whatever value we send doesn't matter. We're not accepting any arguments there.
Since we renamed the parameter in a code to can melee, we need to make sure we update the Blackboard to also be using can melee. Back over in the scene view,
we'll first need a melee attack sensor. Kind of hard to see this one because it's so small, but it's 1.5 unit radius, so really close to that llama. Make sure it's isTrigger and is on your enemy sensors layer and has that player sensor attached. We can drag that one to the melee sensor, keep that to cooldown, and we should be good to go. Let's check out if that works. A little problem here we see is that the llama is constantly moving. Probably most of the time we don't want him to just continually move and attack. Maybe you do. I think it's a little bit weird. I think it might be better if he stops to have to attack. We select the player, we see he's taking a lot of damage. Great. So in our chase, we probably don't want to come here if we are in melee range. For melee range, we're probably close enough we don't care anymore to chase. We can probably just go between idle and melee attack. So we can do that with a second decorator. It's important too that these are evaluated in order. I don't know if I said that earlier. We're going to want to compare to false that they are in chase range and we are not in melee range. Great. Now if we go back to play, we'll see once he gets close enough, he'll stop and then attack. Once I leave the melee range, he starts chasing again. There's always leaving a little bit of space there, so that's great. Next up, I think is everybody's favorite skill, a spit attack for a llama. We're going to follow the same pattern of can do something and is in X range. And maybe here we'll do something like add a new key. So we know we need 2 bools. First one we'll call is in spit range. Second one can be can spit. Once we see we're starting to get a lot of keys, it can be useful to categorize them. Maybe we can put spit related configs under spit. We can put melee related things under melee. And then maybe one for like movement. That's a little bit more organized. I'm gonna go ahead and copy paste the entire melee group because we're gonna do very much similar things to this. But instead of is in melee range, is in spit range must be true, and maybe can spit can be true. Remember that because these are in priority order, once one of these evaluates, we don't need to care about those lower priority conditions because we're going to interrupt whatever's going on the right with whatever we're going to do here. We'll rename the group to be spit attack. I think the attack animation is the same for spit, so we'll wait a second. Instead of on damaging the player immediately, we want to spit out an object, right? We'll delete that, but we will want to do maybe on spit back to ourselves. The only difference between these two is we want to instantiate an object. So drag one down, tasks, object instantiate. What do we want to instantiate? I've made a spit prefab already. We'll take a look at this. We want to set the position and the rotation, so we need to provide those as Blackboard keys. Position needs to be a vector 3 key. I'll call it like spit spawn position. Make sure that's in the spit category. Same for rotation. Rotation needs to be a quaternion key. Now we should be able to select those. Perfect. I guess we can look at the spit object now. This is just a pretty simple mono behavior that'll auto-destroy itself after some time and move with some force. So that means it requires a rigid body and a collider whenever it gets enabled, which we can do on start instead. This is set up so we can use an object pool, but we're just going to use the instantiate functionality from AI tree. So whenever it's enabled, we're going to start a coroutine to delay disable it. We'll create a new wait for seconds if we don't have one, wait a frame, and then add the rigid body force going forward from this object. That's why it's important that we instantiate it with the correct rotation pointing towards the player, or really pointing straight out of the llama's mouth. We'll wait some time and then disable ourselves. This is going to be a trigger collider. So whenever it makes impact with something, we're just going to go ahead and make it be inactive. You can do something simply like maybe where you damage them for, let's say, 13 damage if you hit the player here. Take a look at the spit prefab. We're just using some particles from Unity Particle Pack. It has a simple rigid body with a capsule collider that is trigger, and we have that spit script on it where it'll destroy itself after 1 second, and it's going to move at 100 units of force. Now, to make sure that we have our spit spawning in front of the llama's mouth, let's preview the attack animation about, I don't know, halfway-ish here. Create an empty transform called spit spawn location and position that right around where the spit would come out. Perfect. We'll add a reference to that, hook it up in the inspector, and set those keys based on this object's world space position and rotation. Back to our enemy, we can add something here like references. We'll make a private transform spit spawn location, and on update we can set some Blackboard values. That would be a vector 3 and a quaternion, which we haven't done this stuff here about setting Blackboard values, so let's go ahead and do that twice. One for vector 3, vector 3s all around. And one for a quaternion. I just noticed I left this chase key here for all the variable names, so I'll just do a quick refactor of those key names. We sent the message on spit, so let's define that on spit function. We'll need a last spit time instead of last melee time. So we'll duplicate the last melee time, do a last spit time. Probably need a spit cooldown as well. This is a higher damaging attack. Maybe it needs a higher cooldown. We can finally use the spit sensor, so we'll uncomment those. Now we have set 4 Blackboard keys. The same 2 here about is in spit range. We can spit. And we want to compare the last spit time and last spit cooldown to the time. We also want to set the vector 3 and the quaternion keys, spit spawn position, to be the spit spawn location position. Spit spawn rotation. Okay, so that one seemed like we were doing a lot, but we really just repeated exactly what we just did. So let's go through it again a little bit slower to make sure you got it. At the top, we're now using our spit sensor. We added a new spit spawn location. We added a new spit spawn cooldown. And we added our last spit time so we can use that spit cooldown. We uncommented our on-player enter and on-player exits so we can properly set is in spit range whenever the player enters and leaves that range. We copy-pasted some functions here to allow us to set vectors and quaternions in a single line of code, and then we just are setting these 4 Blackboard keys. Finally, we added a new function that would set our last spit time whenever we receive this callback at the end of our behavior tree chain that we use for spitting attacks. And just remember that we had already set up spit sensor on player exit and enter to set is in spit range true and false based on when the player enters and exits. Coming back to the Unity editor, we can set up our range attack sensor, exact same thing we've been doing so far. We can see it's about halfway between movement, range, melee. We're getting smaller as we get in. So the range attack sensor is the same thing, sphere collider with his trigger with a player sensor, layer on the enemy sensor. We drag that to our spit sensor, make sure we drag our spits on location. Everything else should be good to go. We'll click play, see what happens. The llama's chasing me. Should be in spit range. Aha, there we go. He's spitting at me. Should be another 5 seconds. He spits at me again. Perfect. Everything seems like it's working great. Only 2 more attacks to go, and I think the bounce one is going to be very much the same as what we just saw here. Let's copy paste spit. This one should be a little bit simpler though. We'll call this one bounce attack, connect it up. Remember, we need 2 new conditions. Well, probably only 1 because for bouncing, he's got to be in melee range most likely. So let's do 1 new key, call it can bounce. This is still a melee attack, just a more powerful one. So we'll add that here. So we need to be in melee range, true. And can bounce, true. Instead of playing attack animation, it's going to be a bounce animation. We'll wait. And then instead of instantiating spit, we'll instantiate some bounce particles. This is just for some visual effects. And we don't want to spawn it so high up. It would really be cool if we could spawn it on our location. So maybe we need a new position and we can just use the default rotation. So we probably need 1 more key. We'll make a new one called self position. That's a vector 3 and just spawn it there. So that way it's right there on the ground. And instead of calling on spit on our message, we're going to call on bounce. So again, very much the same things that we've been doing so far. Only difference might be here. We might again want this on damage event. Say it does 15 damage. Auto arrange this, looks a little bit nicer. So we'll damage the player for 15, and then we'll say on bounce is complete. It looks like we have everything we need here because the particle system is hooked up in the behavior tree. All we need to do is set some Blackboard values. We already have is in melee range, so we'll set can bounce. Based on our last bounce time, bounce cooldown, we can define both of those.
Back up at the top underneath the attack configs, we'll make that bounce cooldown with the range from 3 to 20, set the default to be 8. A little bit lower where we have all this last spit time, we'll add a last bounce time.
Down here where we have our callbacks, we can make an on bounce and set the last bounce time to be now. The last one was we need to set the self position, right? Luckily that's vector 3, we can just do transform position. That one should be it. The only thing to keep in mind is our bounce particle systems, we're going to want them to be stop action to be destroy. So that way it goes away once it's played because we don't have a script attached to this one. It's literally just a particle system. It's going to look like that. It's a big bounce. Let's give it a shot. We have to wait at least 8 seconds, staying within melee range. Boom. Perfect. That one was pretty easy now that we have basically everything else already in place. Now last attack is going to be a roll attack, which is obviously the most important attack. I don't think we need any new stuff here other than the roll configuration. So we'll do can roll, like a movement type thing. And I don't know, we'll just copy paste bounce and see what happens. So we don't want to be in melee range. We want to be in chase range. It's going to be a gap closing move. So we want to be, even if we're far away, it's fine. And we want to be can roll. We'll play a roll animation up front. And one thing that AI Tree doesn't have a node for that I kind of wish they did is the ability to enable an object or enable even a component on an object. That doesn't exist here. I did give this feedback to the developer and they promised me that they are working on a lot more out of the box standard nodes. So I'm sure that's coming in an update soon. So we're going to do it with send message to say notify roll start on self. We're going to say on start roll. Argument doesn't matter. What we're going to do there is we're going to enable a collider in front of the llama. Let's look at that now before we get too far into it. There's a roll collider. Let me enable the box collider. We're going to enable this box collider on roll start. So we're just going to toggle here because this is going to be a frozen in place rigid body with this impact sensor that's just going to raise events much like what we just saw. On the player sensor, whenever it makes contact on collision enter, it's going to raise an on collision event. Whenever we receive that, we're going to want to exit out of the roll state. We're going to want to stop rolling, apply damage, whatever. We want this to only be enabled when we're actually rolling. We don't want to constantly be running into stuff whenever we're moving around, because we want to get only events whenever it's actually going to, make us stop rolling. So it should start off with box collider disabled. We'll implement that in just a second. So we'll start that, we'll enable the collider, we'll start rolling. From here, probably we don't need to wait and instantiate anything. Probably what we want to do is start moving faster, because rolling obviously should pick up speed. Let's do a sequencer. Set the speed of the agent to, 6, that's 3 times as fast. Using the nav mesh agent, move to the player's current position. I'm going to not track the moving goal, because maybe we shouldn't be that intelligent about how we're moving. If we're rolling, probably it's harder to do that. So we'll calculate some path, we'll do turns and all that kind of stuff. We just won't continually track the player. It's probably too hard to do that if you're rolling. We'll then wait for the full duration of our animation. It's going to be about 3 seconds. And then we're going to call this on roll, indicating we've successfully completed our roll. We'll also remember to rename our group roll attack, so we don't have 2 bounce attack labels. Now that we've set the speed of the agent, we're going to want to make sure that we set it back before we start trying to actually move. So all the way over, wherever we can move. Let's go ahead and set the speed back to 2, the default speed. This one's a little bit more complicated, right? Let's arrange it. So we're going to enable collider. That's basically what this first one does. Play the roll animation, and then we're going to set the speed, try to move to the player, and then we're going to wait for some time. Remember that move to doesn't say that it's done until it's actually at that location. This wait might be aggressive. We'll see how it ends up looking. Once we've done all of that stuff, so we've made it to the location, we're going to say, okay, hey, we're done moving, which would disable that collider and set the cooldown and all that kind of stuff. Whenever we make impact with whatever this enables, we're going to want to also make sure that we turn this condition can roll to be false. That way we can jump out of here, because this aborts itself on value change. So we can cancel and jump out of this back to whatever state we should go into once we make impact. Let's come back to the enemy. We need an impact sensor. We're also going to need a roll cooldown. And we're going to need to know the last time that we rolled. On start, we need to hook up some events like this, but we just have one here, and that's on collision. So we'll make that. We'll call on roll, which we're going to define here in a second. I'm going to move this down too. It can live with all these other guys. So we're going to set the collider to be enabled false whenever we make contact. And we're also going to set the last roll time to be now. We're also going to set it to be true whenever we start rolling. Instead of trying to do impact sensor get component, I think what I'm going to do is in the impact sensor, just have a public collider. So we'll just reference ImpactSensor.collider.enabled equals false and ImpactSensor.collider.enabled equals true on roll start. And then in the impact sensor, we can just assign that on awake. Make sure that your on roll start and the message you send from the behavior tree are named the same. In this case, what I have on roll start, we need to change to on start roll. Now we're good to go here. And the last thing we should do is set can roll based on our last roll time and our roll cooldown. So if we make impact with something, our last roll time is going to immediately get set to now, which will set this on the next frame update to be false, which will allow us to then, from our behavior tree, exit out of this state. I know that's not the right word for it, but exit out of this section of the tree, because that decorator is going to start returning false, which will allow us to evaluate to a different branch of the tree. That's what's called a branch. We'll get into a new branch of the tree based on whatever other this stuff gets set to be. On our llama, we'll hook up that roll collider, and that should be the only thing we have to do. Make sure your box collider is disabled. We click play. Let's see if we can get a roll to happen where he'll impact something in the world. About 12 seconds, here he comes. There he goes, and boom, came out of the roll and started walking again. Great. All right. And this whole time we can see, I don't know if I can pull this up at the same time. We can see exactly what is this llama doing and why with the visualization of this tree, which is one of the main benefits of a behavior tree, is we can see exactly what it's doing and how it got there. And this was also significantly less code than what we saw when we were doing the state machine, because a lot of the code is hidden behind these nodes that we already have that are provided out of the box.
I know, it's another long one, but I think it was really important to be able to see how you can connect specific implementations of different things like chasing a player, together using something like a behavior tree. Most tutorials, including many of my own, are focused on a very specific implementation of one thing. And then if you're a beginner or even intermediate level developer, it can be really challenging to see how do you connect all these things together. If this video did help you out and you got value out of it, go ahead and like and subscribe, help the channel grow, reach more people and add value to more people. It really helps me a lot. Leave me a comment to let me know that you like this kind of video as well. Now, for this level of complexity of AI, there wasn't really a big difference between doing a state machine and a behavior tree because they're only really doing one thing, right? They're trying to kill the player. If we start thinking more complex AI, like maybe they need to wander around a town, interact with different AI, and also be able to kill the player, that's where things like scope and behavior trees become a little bit more beneficial over a state machine. They become a little bit more easy to maintain. But the key difference from what we did today and what we did with the finite state machine one, really the key benefit of editor tooling in general, is we remove the programmer from having to do everything. We allow somebody who's a game designer and maybe doesn't know how to write code to be able to design the AI behavior and interact in different ways using pre-made things or behaviors that the programmer has put together. Using Unity HFSM while was totally no problem for me because I was the only one working on it and I was the programmer, the designer, the everything. That wasn't a challenge. But then if I bring in a game designer who's going to do way better AI design than I can do, they'll have trouble doing that because then we have to pair to do basically anything. That's really the benefit of editor tools, and I'd really like to thank Renowned Games for giving me the copy of AI Tree today. It was really a great pleasure working with it, and I can't wait to use the more advanced features like the environment query system that I haven't seen available with any other system, and being able to write my own custom nodes. I've got a link to AI Tree in the description. If you thought it was useful and a cool tool to use, you can click on that affiliate link down there. It'll give me a small little kickback. That really helps me out a lot. I've also got links to Humble Bundle. If you want to do your asset store shopping or Humble Bundle shopping, I'd really appreciate it if you're getting value and you're not in a financial position to be able to support the channel through Patreon or YouTube membership. You can just do that. It really helps a lot. If you are getting a lot of value and you do want to show your support directly through Patreon, GitHub sponsors, or YouTube memberships, you can go to patreon.com/LlamAcademy, click join here on YouTube, go to github.com/sponsors/LlamAcademy. Whichever one you choose, you're going to get your name up here on the screen, like the phenomenal supporter Andrew Bowen, Bruno Bozic at the tremendous tier, Autumn K, Matt Parkin, Ivan, Rulin, Iphiobolus, and Solar Int, and Perry at the awesome tier, and all of these other great people at the supporter tier. Thank you all for their support. I am so incredibly grateful.